call is now being recorded. Once again, good afternoon. We are still on the methods of point estimation. The first method that we learned, we have the moments, no? Method of moments, then the maximum likelihood estimation. So this afternoon, we're going to learn the base estimation. Okay. So before going to the method for finding the base estimator, let us discuss first the Bayesian approach to statistics. So in the classical approach, the parameter theta is thought to be a known but fixed quantity. So we have a random sample x sub 1 up to x sub n is drawn from the population indexed by the unknown parameter theta. And then based on the observed values in the sample, the knowledge about the value of theta is obtained. That's for the classical approach. While in the Bayesian approach, theta is being considered to be a quantity. In other words, it's a random variable whose variation can be described by a probability distribution. And we call this distribution as the prior distribution. So this is a subjective distribution based on the experimenter's belief and is formulated before the data are seen. That's why we name prior distribution. So a sample is then taken from a population indexed by our parameter theta, and this prior distribution is being updated with this sample information. Hence, we have the updated prior called the posterior distribution. So the updating is done with the use of the Bayes rule, hence the name Bayesian statistics. So this is actually what we call the Bayesian approach to statistics. Okay, so for our steps, rather for our step, if we denote the prior distribution by pi of theta, and then the sampling distribution by this joint PDF or the joint PMF, then the posterior distribution, which is actually the conditional distribution of theta given our sample x. So it's being denoted by pi of theta given x. So this is now the conditional distribution of theta given the sample x. We call this as our posterior distribution. And it is equal to this fractional expression in which the numerator is actually the product of the joint PDF or PMF of our sample and the prior distribution divided by m of x, where the m of x is the marginal distribution of x, and we can obtain this marginal distribution of x by integrating out theta in this expression, no? The integral of the product of the joint PDF or PMF of our sample times the prior distribution uh, d or d theta. So this expression, which is the product of the joint PDF or the joint PMF and the prior distribution, can be expressed as f of the sample x and theta. Okay, so notice that the posterior distribution is a conditional distribution. Ah, is a conditional distribution. Rather, it's a conditional distribution, conditional upon observing the sample x or the sample. So the posterior distribution is now used to make statements about our parameter theta. This posterior distribution still good. In other words, rather the mean of our posterior distribution is being used as a point estimate of our unknown parameter theta. Okay, we have here a note on notation when dealing with distributions on the parameter theta. We will break our notation convention of using uppercase letters for random variables and lowercase letters for arguments. Thus, we may speak of a random quantity theta with distribution pi of theta, okay, referring to the prior distribution. By the way, in our example here, it's not actually an illustration of our uh, steps here above, because I just want to emphasize here that we have a joint PDF or a joint PMF of our sample. Since we know that the sufficient statistic, no, our sufficient statistic contains all the information about our unknown parameter that is in the sample, and it depends only through the value of our sufficient statistic. So we can replace our joint PDF or a joint PMF here by the distribution of our sufficient statistic. So kung meron tayong y here, lagyan ko na lang, no? Kasi ito yung ginamit sa example. Say we have here y, sufficient statistic siya. Alam naman natin paano kunin itong sufficient statistic based on our the based on the previous chapter, y being a sufficient statistic. So it has a distribution, a sampling distribution. So we can replace our joint PDF or the joint PMF of our sample by the distribution of our sufficient statistic. So ito ngayon, we have now this conditional distribution of theta given our sample x. So pwede na natin sabihin the conditional distribution of our unknown parameter theta given y. Okay, that's the value of our sufficient statistic. And we have now f of y given theta times the prior distribution of our parameter of our theta divided by this marginal distribution of y, m of y. So we have now here m of y would be equal to this integral of f of y and then pi of theta d theta. Okay. So let us illustrate this using our example. We have the binomial base estimation. Take note, for us to be able to estimate our unknown parameter theta, we're going to find first the posterior distribution, and the mean of that posterior distribution would estimate the unknown parameter theta. So let x sub 1 up to x sub n be IID, okay? Random sample or a random sample coming from a Bernoulli distribution with probability of success P. Then we have here y, which is equal to the summation of x sub I, has a binomial distribution with n number of trials, and the probability of success is P. We know before, no, in chapter 6, that this y is a sufficient statistic. Which is actually a function of our sample for a function of our random variables x sub 1 up to x sub n. As I have said, the sufficient statistic contains all the information of our unknown parameter p on a given sample. So we assume our prior distribution on p having a beta distribution with parameters alpha, beta. So if we're going to determine the joint distribution of our sufficient statistic y and p, so we have here. Ito yung ginamit natin, no? So para tayong merong y given theta, times the prior distribution of theta. So we have f of y theta. So instead of using our sample having a Bernoulli distribution, we manipulate, no? We use our sufficient stat in order for us to determine our Bayes estimator. Okay, so we have now our joint distribution of y and p. So this is the uh, pwede natin sabihin, this is the sampling distribution or the distribution of our uh, statistic y, okay, given our parameter p, and then we have here the prior distribution of our parameter p. So ito yung sa binomial, because y has having a binomial distribution. So we have here a combination of n taken y, and then the probability of success p raised to y, probability of failure 1 minus p raised to n minus y. Okay, so ito yung sa distribution of our y, sufficient statistic y. And then since p has a beta distribution with parameters alpha beta, then ito yung kanyang distribution. Okay, ito yung kanyang distribution. So we have here gamma of alpha plus beta divided by gamma of alpha, gamma of beta. Then we have p to the alpha minus 1, 1 minus p raised to beta minus 1. So if you're going to determine the product of these two distributions, so we have here on the second equality. So using the law of exponents, we have here p of y and then p of alpha minus 1. So we have p of no p raised to y plus alpha minus 1. We have that result. And then we can also have this 1 minus p raised to n minus y, 1 minus p raised to beta minus 1. So we have this product. And then we copy the remaining terms or in the remaining factors. So we have the combination of n taken y, and then we have this fractional expression of the gamma of alpha plus beta divided by the product of gamma alpha and gamma beta. Okay, so this is now our joint, no? The joint distribution of y and p. So if we're going to determine the marginal PDF of y, in other words, we're going to integrate out p. So we have here. So instead, no, f of y yung ginamit niya dito, supposedly it should be m of y. No? Parang sabihin na natin m of y dapat ito. Pero okay lang din naman. Wala naman problema yan. So, pero kung consistency yung gagamitin natin, so what is we actually m of y? Okay, so we have that. We integrate out p, and then our parameter space is actually the p value is between 0 to 1 inclusive. So we have here the joint distribution of y and p dp evaluated from 0 to 1. And then we have these results. Okay, this is actually a distribution known as the beta binomial. Parang in-integrate natin dito, no? Itong part na to. Ito siya dito, we integrate it. So in other words, pwede tayong mag-multiply by a quantity equal to 1. So ano itong quantity na i-multiply natin dito? Parang nag-multiply lang tayo dito, no? A quantity equal to 1. So we have here gamma. Ito yun, no? Y plus alpha. And then we have n minus y plus beta. So we have here gamma of y plus alpha okay, plus n minus y plus beta. You divide it by gamma of y plus alpha, then gamma of n minus y plus beta. And then you divide it by the same expression. So we have here gamma of y plus alpha plus n minus y plus beta divided by gamma of y plus alpha and gamma of n minus y plus beta. Okay? So kung i-integrate natin yung joint distribution of y and p with respect to p, no? Integrate out p. So parang itong expression na to, ibang color tayo na light. Anong gagamitin natin? Si yellow. Ito, isama natin ito. Okay, isama natin ito. Ayan. Tapos may integral tayo from 0 to 1 and then we have dp. That would equal to 1. So may iwan ito, itong part na to. Ito, yung sa itaas natin, itong expression y plus alpha plus n minus y. So in other words, y here will sum equal to 0. So may iwan sa numerator natin na alpha plus beta plus n. Take note, no? Take note. In our joint distribution of y and p, we multiply a quantity equal to 1. So ito yung nasa pink, yung pink na yan. This is a quantity equal to 1. So parang pareho lang pa rin yan sa ating joint distribution of y and p. And then if we're going to integrate that joint with respect to p, so the integral of yung naka-yellow na yan, dp, from 0 to 1, that would be equal to 1. So yung naiwan, itong pink na to, nasa denominator naman siya. Lagay natin sa numerator, so yung reciprocal. So kaya yung nasa itaas, ito na ngayon, ito na pumunta na dito sa numerator. Yung sa ibaba, we have now n plus alpha plus beta. May iwan pa rin ito. That's why we have that. Okay, so we have a beta binomial distribution for the marginal PDF of y. And then solving for the posterior distribution of y given p, kung posterior naman tayo, it should be pi of p given what? Kung consistency lang yung gagamitin natin na notation, ha, kasi sa itaas we use pi of theta. Okay, we use here pi of theta for the prior distribution of our parameter theta, and then pi of theta given the sample x for our posterior distribution of theta. As I've said, if we use the sufficient statistic, so yan yung blue yung gagamitin natin. So ang ginamit dito sa solution actually, sa example 7.2.14, we use the sufficient statistic, not necessarily yung ating, in-apply natin yung ating sample, random sample. Okay, so the posterior distribution now, we have this fractional expression, the joint of y and p given divided by the marginal distribution of y. So kung titingnan man natin ngayon, ito yung ating Ito yung ating joint. Ito yung ating marginal. Okay? M of y yan siya, no? Marginal, M of y. So, parang, kan lang, no? You do not look at this quantity equal to 1, itong pink na expression dyan. So, magka-cancel out yung combination of n taken y, obviously. Magka-cancel yung gamma of alpha plus beta. Magka-cancel yung gamma of alpha and then gamma of beta. No? Kung titingnan natin itong fractional expression, no? F of y over p. So yung may 1, ito, gamma of n plus alpha. Nasa denominator, obviously ito, supposedly itong m of y nasa denominator. So reciprocal niya, so we have gamma of n plus alpha plus beta divided by gamma of y plus alpha, gamma of n minus theta. So yung maiiwan pa rin ito, part na to. Kan lang ha, i-delete ko lang. For example, ito yung f of y. Ito ang m of y. So cancel ito. Cancel yan. Cancel ito. Cancel yan. E nasa denominator naman ito. Nasa denominator. Okay, nasa denominator ito siya. So ito nasa numerator. So ito yung may iwan expression. Okay, so kung ko lang delete ko lang yan kasi i-erase ko lang. Nakuha nyo ba, guys?
Okay lang, sir.
Okay lang? Okay, so we have that as our posterior distribution. This posterior distribution has a beta distribution with parameters y plus alpha, n minus y plus beta. Okay, so if we want to estimate our parameter p, which is the probability of success, if we're going to determine the mean of our posterior distribution, so ano yung mean ng ating posterior distribution? Sabihin natin, no? The mean of our posterior distribution yan, the mean of that is actually equal to y plus alpha divided by y plus alpha plus n minus y plus beta. That's the mean of our posterior distribution. And that is equal to y plus alpha over alpha plus beta plus n. And the mean of our posterior distribution is actually the base estimator, or rather the base estimate of our parameter p. So this is now the base estimate. Base estimate lang siya. So if you want to find the base estimator, therefore, the base estimator of our parameter p is what? What do we have? Y plus alpha over alpha plus beta plus n. So ito yung random variable yan siya. because our estimator is a function of the sample, and y is also a function of the sample. That's why we have that. Ito, base estimate, no? It's the base estimate of our parameter p. Actually, sabi niya dito, which would give us the base, no? Which would give us the base estimator of P. Not the estimator, it's actually the base estimate of P. Kasi itong Y dito is the realized value of our statistic Y. So it's the base estimate of P. But if we're going to find the base estimator of P, so it should be capital Y plus alpha over alpha plus beta plus N. Okay, so any questions or clarifications?
Sir, sir, kung mag-answer ni Ana, sir, for example, base estimate, then estimate, base estimator. It's just simple as making the Y capital letter.
Yes. Kasi pag sabihin natin na estimator, it's a random variable. So, because an estimator is a function of the sample, a sample is actually, sabihin natin we have these random variables, x sub 1, x sub 2, up to x sub n. Yung realized value ng ating sample, yung mga small letters na x sub 1, or yung realized value ng ating statistic, say in this case, our statistic is the y, capital Y, which is actually a sufficient statistic, no? Sufficient statistic. So yung kanyang realized value, the small y. So ibig sabihin nito, kung meron tayong realized value ng small y, this is the estimate, no? The estimate of our parameter p. Pero pag estimator yung hinahanap, it's actually a formula. No, it's a formula. So that's actually a function of your sample. So y is here, y is a function of the sample because it's equal summation of the x sub I. Okay, so this is our, so the whole expression is the base estimator of P. Meron lang may nag-emphasize lang ako dito ng mga things na sa solution niya. Para consistent lang sa mga notations niya na ginamit dito sa itaas, yung prior niya, pi of the parameter, okay, pi of the parameter, yung kanyang sampling distribution, it's either the joint PDF or the joint PMF of the sample. And then yung posterior distribution niya, we have the conditional distribution of theta given x. So pi of theta given x. So pi yung ginamit. Pero pwede ka naman, no? Walang problema actually itong mga ginamit niya na mga notations. Kung naiintindihan lang, no? Baka kasi yung iba nalilito sa paggamit ng mga notation. For consistency's sake, kaya meron ako mga parang sinabi kong corrections but not necessarily correction. Kagaya dito, no? Kagaya dito, yung marginal PDF ng Y, f of Y yung ginamit, pero according to our notation above, it should be M of Y. Then dito naman, I hope na intindihan nyo dito sa part na to, kasi alam natin na ang sufficient statistic contains all the information about the parameter in the sample. So instead of using the sample, we can use the sufficient statistic. That is why we have here the conditional distribution of our parameter given the value of our sufficient statistic, which is small y, and that is equal to the product of the distribution of the distribution of y times the prior distribution of the parameter divided by the marginal distribution of y. Hindi kasi na-illustrate itong part na to sa example kasi sa example ang ginamit yung sufficient statistic. Okay lang ba? Naintindihan lang ba?
Yes, sir.
Okay. Just want to emphasize here that our base estimate of our parameter P, ito na, base estimate of our parameter P, it could be written as a linear combination of the prior mean. So in this case, saan dito yung prior mean natin? This is the prior mean because the prior distribution has a beta distribution. Tapos yung mean ng ating beta distribution having the parameters alpha, beta. So we have here alpha over alpha plus beta. So this is the prior mean. And the sample mean. This is the sample mean because our y here is actually the summation of the x sub i's. So if we divide that by n, divided by n, divided by n, this is equal to the sample mean. And then the weights being determined by alpha plus beta plus n. So in other words, our base estimate, this base estimate, ito siya, no? Itong part na to, pwede natin na-express as a linear combination of the prior mean and the sample mean. Says here, no, consider how the base estimate of P is formed. The prior distribution has mean alpha over alpha plus beta, which would be our best estimate of P without having seen the data. Okay, that's the best estimate of P without having seen the data. So ignoring our prior information, we would use P equal to y over n. The P is the probability of success. Our y, which is the summation of x sub I having a binomial distribution, that means y is actually the number of successes. So the number of successes divided by n, here, the number of successes divided by n would be our estimate of the probability of success P. So the base estimate of P combines all this information. Okay, so okay, so in the above problem, we actually choose the prior distribution that comes from a beta family. Yung P natin has a beta distribution. And then, anong reason dito ba't ginamit natin yung beta distribution? Because we can obtain a closed form expression for our estimator. Gaya dito, no? A closed form expression for our estimator. So in general, for any sampling distribution, there is a natural family of prior distributions. We call it as the conjugate family. So we have here in definition 7.2.15, we let script F denote the class of PDFs or PMFs indexed by our parameter theta. A class big pi of prior distributions is a conjugate family for script F if the posterior distribution is in the class big pi for all, no, for all PMF or PDF small f and all priors, no, in big pi and all x in our sample space. So ibig sabihin yan, kung yung prior distribution natin belongs to this family, then our posterior distribution must also belong to that family. Nakita natin sa ating example above na yung prior distribution natin has a beta distribution, and we have seen that our posterior distribution has also a beta distribution. So the beta family is a conjugate for the binomial family. Thus, if we start with a beta prior, we will end up with a beta posterior. So the updating of the prior takes the form of updating its parameters. So mathematically, this is a very convenient, for it usually makes a calculation quite easy. So we end up this section regarding the base estimation with another example. So we have the normal base estimators. So we let X here having a normal distribution with mean theta and variance sigma square. And then suppose that the prior distribution of our mean theta is also normal with mean mu and variance tau square. So here we assume that our sigma square, our mu, and our tau square are all known. So yung unknown lang dito sa problem na to, yung ating parameter theta. But fixed, no? Unknown but fixed. With regards to our sampling distribution of X are all known. So the posterior distribution of theta is also normal with mean and variance given by, ito lang, diretso kaagad. Ito na yung binigay sa atin ng book. You see that in exercise 7.22 for details. So I'm going to give you this as one of your problem set. Verify that our posterior distribution of our parameter theta is also normal with the corresponding mean and variance. So in other words, no, if we're going to verify it, we have our prior distribution. Okay, our prior distribution, we have pi of the parameter theta, okay, having a normal distribution. Na itong sabi niya, with mean mu and variance tau square. So we have here 1 over the square root of 2 pi tau square. Okay? At tau lang pala. Hindi man naka 2 pi tau, the exponential function of the negative of theta minus its mean quantity square divided by 2 tau square. Okay? Yan yung ating prior distribution. Take note, sampling distribution. It should be sampling distribution. Itong case na to, no? This is a sampling distribution. Itong part na to. Kuha na natin. Ito. The joint PDF or the joint PMF. That's the sampling distribution. Sampling distribution by. Pero dito sa problem na to, sa example natin, 7.2.16, wala naman tayong random sample na ibigay dito sa problem na to. What we have the random variable x having a normal distribution with mean theta and variance sigma square. Parang ina-assume natin dito na meron tayong random sample x sub 1 up to x sub n IID coming from a normal distribution, okay, with mean, mamaya ko lang isulat yung yung variance niya with mean theta, wala, hindi ko na sulat. Tapos ito, this is what we call the sufficient statistic. Ito ngayon yung tinatawag natin na sufficient statistic. In our previous discussion, ano yung sufficient statistic natin? If we have a random sample coming from a normal distribution. Ano nga yun? In our previous discussion?
Sample mean, sir?
Yeah, that's correct. We have the sample mean. So kung ito yung given n has mean, theta, and variance sigma square, yung sample mean natin has a normal distribution with mean theta, but in this case we have sigma square over n, yung variance niya. So kung ito yung given ngayon, ito ngayon actually, this x here is the sufficient statistic that referring to the sample mean. Kaya wala siyang random sample na ibinigay dito sa problem na to. No? In that case. So, sufficient statistic na lang. Yan yung sufficient statistic. So, instead of using the sampling distribution slash, okay, sorry. Slash na lang ito, we have the distribution. Yung distribution of the sufficient statistic. So, ano yung distribution ng ating sufficient stat? Sufficient statistic yung itong x. Itong x. So, we have now f of x given our parameter theta. So, in this case, we have a 1 over the square root of 2 pi sigma, okay, the exponential function of the negative of x minus its mean, ano yung mean niya, theta, quantity square divided by 2 sigma square. Okay, so meron na tayong prior, meron na tayong distribution of the sufficient statistic. So hahanapin natin yung joint distribution of x and theta. So we have here f of x and then here theta. So it's actually f of x times the posterior distribution. Yan yung hahanapin nyo. And then after that, you're going to solve for the verification. Then you're going to solve for the marginal distribution of x. Then after that, we're going to solve for the posterior distribution. So yung posterior distribution natin, you have pi of theta given x. So, etong posterior distribution, meron siyang normal distribution. Yun yung sabi dito, meron normal distribution with mean. Sabihin na lang natin mu asterisk and variance sigma asterisk square. Where yung ating mu asterisk is equal to this. Yan yung mean of the posterior distribution. Itong variance ng ating posterior distribution is equal to sigma asterisk square. Okay, so we have that. Yan yung kanyang flow in order to show that we obtain the mean and the variance of this posterior distribution. So I hope na naintindihan nyo ngayon dyan by this example, no? And the first example regarding the base estimation procedure. Take note, no? Mas madali tayong mag-evaluate or mag-determine ng ating base estimators if we're going to use the sufficient stat rather than no, uh, the sample, which is the random sample or the random variables x sub 1 up to x sub n. So very crucial yung factorization theorem, ano pa yung mga ginagamit natin in the previous chapter to obtain our sufficient statistic. Okay? PS to, problem set, no? Isa. Notice that the normal family is its own conjugate family. So again, no? We have a prior distribution coming from a normal family, and then we obtain in this example the posterior distribution also belongs to the normal family. So again, using the posterior mean, we have the base estimator of our parameter theta. Here, the mean of the posterior. So therefore, ang conclusion dyan, kung ang hinahanap ko, ang tanong sa inyo, ano yung maximum, ano yung base estimator of the parameter theta? Therefore, the base estimator of theta is, ito ngayon, we have tau square over tau plus sigma, tau square, sigma square. We have capital X. Capital X. Kasi ito, estimate ito. It's a realized value of our estimator plus sigma square over sigma square plus tau square. Kaya nga ito, pinalitan siya ng capital X. Ito. Capital X. So ito, palitan mo itong small x yan by capital X. That's the base estimator. So the base estimator is again a linear combination. Okay, the linear combination of the prior mean and the sample mean. That is why yung tanong ko kanina, yung sufficient statistic natin dito, it actually refers to the sample mean. Kaya makita, this is the sample mean. Kaya yung x dyan is the sample mean. Diba? Oh, it is a linear combination of the sample mean. So ito yung sample mean. Ito, sample mean. X bar, di ba? Yung sufficient statistic is the sample mean. And the prior mean. So ano yung prior mean? Kung yung theta has a normal distribution with, yung given naman sa prior, yung mean niya, mu, here. Prior mean. So ito yung mu. Yellow na lang na yellow. Tsaka yan. Sample mean, capital X, and the prior mean, which is mu. Okay? Any questions or clarifications before we go to the next method? None?
Wala, sir.
Okay, so the next method we have here an EM algorithm. This is actually a reading assignment, but I'm going to explain to you, but not thoroughly, no, on saan nagakahitabo aning EM algorithm. Though it will not be included in the exam, but somehow very important, no, itong algorithm ito because makikita natin usually ito sa mga paper. So a last method that we will look at for finding estimators is inherently different in its approach and specifically designed to find the maximum likelihood estimators. Rather than detailing a procedure for solving for the maximum likelihood estimator, we specify an algorithm that is guaranteed to converge to the maximum likelihood estimator, or converge to the maximum likelihood estimate. So this algorithm is called the EM algorithm, or the expectation maximization algorithm. It is based on the idea of replacing one difficult likelihood maximization with a sequence of easier maximizations whose limit is the answer to the original problem. It is particularly suited to missing data. So baka yung iba dyan, no? Yung kinang paper nila sa MS, we have this having a missing data. So we have missing data problems, as the very fact that there are missing data can sometimes make calculations cumbersome. So however, we will see that uh, filling in the missing data will often make the calculation go more smoothly. So in using the EM algorithm, we consider two different likelihood problems. So the problem that we are interested in solving is the incomplete data problem. And the problem that we actually solve is the complete data problem. Mas mahirap naman, mas mahirap kasi minsan mag-evaluate if we have an incomplete data. So we solve using the complete data. So depending on the situation, we can start with either problem. So we have an example here. We have the multiple Poisson rates. We observe x sub 1 up to x sub n and y sub 1 up to y sub n, all mutually independent, where the y sub I has a Poisson distribution with rate, beta, tau sub I. So it's a function of tau sub I, yung rate ng ating Poisson distribution. And then the x sub I here has a Poisson distribution with rate tau sub I. So this would model, for instance, ito yung application niya, the incidence of a disease. See, y sub I, where the underlying rate is the function of an overall effect, beta, and an additional factor, tau sub I. So for example, tau sub I could be a measure of population density in area I, or perhaps health status of the population in area I. So we do not see tau sub I, but we get that information through x sub I. So ito yung paraan for the EM algorithm. The joint PMF is therefore, okay, so we have here two random samples. So we have an ordered pair, x sub 1, y sub 1, x sub 2, y sub 2, up to x sub n, y sub n, given our parameters now. So the parameters are beta, then tau sub 1, tau sub 2, up to tau sub n. So the joint will just be this finite product of this. Ito yung sa Poisson distribution, no? Ito yung sa Poisson distribution of our random sample y sub I, no? Our random sample y, bold y. And then this is for the random sample bold x. Yan, Poisson naman. E to the rate, the negative rate, and then the rate raised to y sub I given y sub I factorial. Same thing with for the random sample x. So we have that product. So the likelihood estimators, okay, so yung likelihood natin is a function of our parameter, and that would be equal to our joint PDF. But we are taking our parameter to be unknown and our sample fixed. Ito fixed ito. Kasi it's a function of the parameter. Yung ating likelihood function. Kasi yung sa likelihood function, di ba sabi natin yung likelihood function L is a function of the parameter given. No? Parang ganun. The function of our parameter theta given our sample X equal to the joint PDF. Parang ganun. But this we consider here to be a function now of the parameter theta, because x here is fixed. Pero per se, di ba yung in-explain ko per se, kung ito lang, hindi yan siya likelihood o joint PDF yan siya, this is actually a function, no? A function of the sample, yung PDF natin, o yung joint PDF. Given ito, eta, unknown siya, but fixed. So, ganun din dito. So, we can apply the straightforward differentiation. So, we have a system of equations. Then we equate all this differentiation to zero. So, we have system of equations. And then solve for the maximum likelihood estimate of our parameters. Beta, tau sub 1, tau sub 2, up to tau sub n. So ito yung estimate. This is the estimate. Estimate siya. This is an estimate. Maximum likelihood estimate of beta. Kasi small letter man ito. And this is the maximum likelihood estimate of the tau sub i's or tau sub j's. J from 1 up to n. So the likelihood based on the PMF 7.2.11 is the complete data likelihood. Okay, so this set of ordered pairs, x sub 1, y sub 1 up to x sub n, y sub n will be called the complete data. So kung meron tayong missing data, which is actually a common occurrence, would make estimation more difficult. Suppose, for example, the value of x sub 1 was missing. We could also discard y sub 1. Pwede natin discard ng y sub 1 and proceed with a sample of size n minus 1. Sabihin natin na complete siya. Pero ang sabi dito, but this is ignoring the information in y sub I. Kung ganun yung gagawin natin, we are ignoring the information that y sub I can give to our unknown parameters. So using this information, we will improve our estimates. Kung kasali ito, we'll improve still our estimate. So kung meron tayong missing data, this would be starting from the PMF 7.2.11. Now the PMF of the sample with x sub 1 missing is, so we have here the infinite summation of the joint PMF. So kung i-express natin itong joint PMF dito, this is actually a product, no? The summation of the product. Mas mahirap siya i-evaluate. So the likelihood based on 7.2.13 is an complete data likelihood. This is the likelihood that we need to maximize. So in general, we can move in either direction, from a complete data problem to the incomplete data problem, or the reverse. So if we have y sub I, rather if bold y, we have a sample here, y sub 1 up to y sub n are the incomplete data. O incomplete data yan siya. And then bold x here, this is a vector of random variables, are the augmented data. So we are making this pair, yx, the complete data. And then the densities, g dot given theta for y, bold y, and then the conditional, I'll say this density f dot given parameter theta for the joint, the joint of y and x. We have this relationship now in 7.2.14, and replacing the sum. Now we can replace the integral by sums if we have a discrete case. So if we turn this into likelihoods, so the likelihood of our parameter theta given y would be equal to this PDF g of y given theta. This is for the incomplete data likelihood. And then the likelihood of the parameter theta given y, no, some observed sample y and x will be equal to this joint PDF also, given the parameter f of yx given theta, that is for the complete data likelihood. So if the likelihood function of theta given y is difficult to work with, it will sometimes be the case that the complete data likelihood will be easier to work with. Yung example nito nasa book na, so you can continue reading. But I just want to emphasize here na itong EM algorithm is usually being used if we have missing data. Okay, so let us proceed to the next section of chapter 7. We have methods of evaluating estimators. We have different method of determining the point estimators of our unknown parameter. We have the method of moments. We have the maximum likelihood estimation. Uh, we have also the Bayes estimation. We have also the EM algorithm estimation procedure. Pero yung, kung kahit sa tatlo na lang, the first three procedures, they may or may not have the same estimators for our unknown parameter. For our unknown parameter. Sabi ko, pwedeng pareho sila or pwedeng hindi pareho yung kanilang mga estimators for our unknown parameter. So in this section, we're going to introduce some basic criteria for evaluating estimators. Kasi pwede naman marami yung mga estimators for our particular parameter. Siguro for the method of movements, ito yung kanyang estimator. Magkaiba siya sa maximum likelihood estimator. Magkaiba din siya sa kanyang Bayes estimator. So we're going to evaluate these estimators and examine several estimators against these criteria. The criteria for evaluating estimators. So the first one, we have the mean squared error. We first investigate the finite sample measures of the quality of an estimator beginning with its mean squared error. So the mean squared error, we have MSE of an estimator of a parameter theta is a function of theta defined by, okay, it's a function of theta, which is the expectation of the square difference of the estimator and the parameter theta indexed by our parameter theta because it's a function of theta. Some other books will have this notation, pwede nilang ganito yung kanang, we have now the MSE of our estimator W will be equal to the expectation of W minus theta squared indexed by theta because it's a function of theta. Ito dito sa book hindi ito ginamit na part na to. Pero pwede natin gamitin. So the MSE of our estimator W. Okay, so notice that the MSE measures the average squared difference between the estimator W and the parameter P. Kasi yung expectation dyan, pwede naman sabihin natin it's the mean. It's the mean of the square difference of the estimator and the parameter. Iba yung expectation considered as the mean. So itong square difference of double theta is actually a distance measure. Square. So kung kukunin mo yung average of all these distances or the square of this difference, W minus theta. That's actually the mean square error of that estimator. We can have also another distance measure, say the absolute difference. no? The absolute distance here. So the absolute value of the estimator minus theta. So the mean square, the mean, we call this as, to serve the measure of goodness of measure, we have what we call the mean absolute error. So this is an alternative also, no, measure. Ang sabi lang dito, the MSE has at least two advantages over other distance measures. First, it is quite tractable analytically, and second, it has an interpretation that the MSE of our estimator W is equal to the variance of our estimator W plus the square of the expectation of our estimator W minus its parameter theta. Or in other words, it is equal to the variance of our estimator W plus the square of the bias of our estimator W. Kaya parang ma-define natin yung bias natin. The bias of our estimator W is somehow equal, is rather equal to this difference. The expected value of W minus the parameter theta. So if the bias is identically equal to 0, okay, the bias is equal to 0, kung ito equal to 0, ito equal to 0, so the expectation minus theta, this would imply that the mean of our estimator W will be equal to our parameter theta. Ito ngayon nakuha natin. Then we have an unbiased estimator W. So unbiased na siya. An estimator is called an unbiased, and it satisfies that the mean or the expected value of that estimator is equal to its parameter theta. So we have two components for our MSE. The first component, measuring the variability of our estimator, it talks about the precision of that estimator. And the other one, measuring its bias, that's for the accuracy of our estimator. So an estimator that has good MSE properties has small combined variance and bias. So to find an estimator with good MSE properties, we need to find estimators that control both variance and bias. So clearly, unbiased estimators do a good job of controlling bias. Kasi ang bias is equal to 0. And then for unbiased estimator, then the MSE. Pwede na lang sulat ko dito ha. Then the MSE of our estimator W. Okay, say we have this index by our parameter theta is equal to this. So for an unbiased estimator, then we have it is equal to the variance of W. And so if an estimator is unbiased, the MSE is equal to its variance. Okay, let's have an example. We have the normal mean squared error. So let x sub 1 up to x sub n be IID, normally distributed with mean mu and variance sigma square. We know that our statistics sample mean and the sample variance are both unbiased estimators since, okay, ito naman yun, no? Our sample mean is normally distributed with mean mu and variance sigma square over n. Ayan. Alam natin before na sa STAT 331 yung mga distribution ng ating sample mean, no? Sampling distribution of our sample mean as also our sample variance. Tutunan natin yan dun. So we have here the mean of the sample mean is equal to mu. The mean of the sample variance is equal to sigma square. Okay, so since it is equal to the unknown parameter, then the x bar and s square are both unbiased estimators. So if we're going to uh, compute for means, the mean squared error of our estimators. So ito ngayon, we have here the MSE of our sample mean, okay, based on our parameter mu equal to that. Pwede yung ganun, no? Yan yung ating definition. The expectation of the squared. Hindi na nga sinulat dito yung subscript na mu, no? Supposedly, meron tayong subscript na mu dyan. Okay, so here, obviously, this by definition, yung second equality, this by definition, since we know na uh, unbiased estimator, yung ating sample mean, so bias natin 0, then that will be equal to the variance of our estimator x bar. So ano yung variance ng ating estimator x bar? That would be equal to sigma square over n. Okay, here. And then the mean squared error of our sample variance. Here, our parameter is sigma square. Kaya may mu diyan, no? Dito meron sigma square, meron sigma square. Pwede na ganun. Pwede na wala. Walang problema dyan. So, that is equal to the expectation of this. Okay? Since we know unbiased ito, yung S square natin, so yung bias equal to 0, so that will be equal to the variance of the estimator, S square. And we have seen this in theorem 5.2.6. Then we have the answer for the variance of the sample variance. 2 sigma to the 4 over n minus 1. So the MSE of the sample mean remains sigma square over n, even if the normality assumption is dropped. We have seen this before, no? We have a theorem in which alam na natin na IID yung random sample natin, having a mean mu and a variance sigma square. The mean of the sample mean is still equal to sigma square over n. Nasa SPAT 331 yan. So however, the above expression for the MSE of the sample variance does not remain the same if normality assumption is relaxed. It's not true. So although many unbiased estimators are also reasonable from the standpoint of MSE, be aware that controlling bias does not guarantee that MSE is controlled. Control bias does not guarantee also that we will get a small MSE, mean squared error. So in particular, it is sometimes the case that a trade-off occurs between variance and bias in such a way a small increase in bias can be traded for a larger decrease in variance, and it will result to an improvement in our mean squared error. We have here an illustration in example 7.3.4. So we have an alternative estimator for our parameter sigma square. We have the maximum likelihood estimator. Na-solve natin ito before. So we have here sigma square hat. By the way, parang pareho lang yung pagka-express ng estimate at saka estimator. Parang ito, kung small small ito na mga variable, small x sub I, and then small x sa sample mean, yung ganun yan. Yung sigma hat square is an estimate. Pero pag capital siya, variable siya, or random variable, then we call that as the estimator. Ganun pa rin yung ating ginamit, no? Pero kung sa MGB na book, iba talaga yung notation nila. Ito, pareho lang. So we have here our maximum MLE estimator, sigma square hat. And then it is equal to n minus 1 over n times the sample variance. Okay? sample variance. So it is straightforward to calculate. So if we're going to determine the mean, the mean of this estimator, sigma square hot, that's actually the expectation of n minus 1 over n times the sample variance S square. Okay, it is straightforward because this is equal to, so by n, we have here the expectation of S square. Then from above, the expectation of S square is equal to uh, sigma square. The mean of S square is sigma square. So we have that. Uh, Looking at this result, the expectation of this estimator, sigma square hot, is not equal to its parameter, sigma square. We have n minus 1 over n kasi, times the sigma square. So the estimator, sigma square hot, is a biased estimator of sigma square. And then the variance of the estimator, sigma square hot, can also be calculated. So we have here the variance. We just, first equality, we just substitute what is sigma square hot. Ito yun. And then the next equality here, we apply the property of the variance. So that's why the square of n minus 1 over n times the variance of S square. And then using the variance of S square above, ito yun, variance of S square above, 2 sigma square over n minus 1. So mag-cancel out yung n minus 1. So may iwan sa itaas, yung n minus 1 na lang. So n square pa rin yung sa denominator. Kasi ito siya, equal ito sa 2 sigma square over n minus 1. Ito, mag-cancel dito. So yan yung maiiwan. Okay? So that's the variance. Therefore, the MSE, sabihin natin, yung MSE ng ating estimator, sigma square hot, equal to that. It's the expectation of the square difference of the estimator minus its parameter. Okay, so this is the what we call the variance of our estimator. No? Ito yung variance ng ating estimator. And this is the bias. Ano yung bias? Ang bias is the mean of the estimator. Ito yung mean ng estimator natin. Mean of the estimator minus the parameter. You square that. You square the bias. And then simplifying. Okay, simplifying, then we have these results. Okay, madali lang ito, no? Pag-simplify. Kasi dito, n, ito siya part na to, at 1 lang naman yan. So positive sigma square minus sigma square, that would be 1. Rather 0. So yung maiiwan na lang, sigma square over n. So itong part na to is you're going to simplify this. The result would be the negative of sigma square over n. So if we're going to square that one, i-square pa natin ito, then we have sigma to the 4 over n squared. Eh, magkapareho na yun sila dito, yung denominator natin sa variance. Okay, so simplifying, then we have that results. So yan yung variance ng ating estimator sigma square hot. And hence, the MSE, it's the MSE rather. Ito yan, yung MSE. Okay, so ito ngayon yung ating the mean squared error of the maximum likelihood estimate of our parameter sigma square. Ito, equal ito sa mean squared error of our sample variance S square. Okay, showing that the estimator sigma square hat, it has a smaller MSE than the estimator S square. Ito siya unbiased. Ito siya biased na estimator. So thus, by trading off variance for bias, the MSE is improved. Yan yung sabi kanina, not necessarily that you're going to control the bias. It will not guarantee us that we have a smaller MSE. That is why we have this example. Na meron tayong bias na estimator, but we obtain a smaller MSE compared to the unbiased estimator. In general, since MSE is a function of the parameter, there will not be one best estimator. Often the MSE of the two estimators will cross each other, showing that each estimator is better with respect to the other in only a portion of the parameter space. However, even this partial information can sometimes provide guidelines for choosing between estimators. Okay, so we have actually another example here in which meron siyang we have two MSEs, no? Mean squared errors of our two parameters. In some parameter space, ang isa ka estimator is better compared to the other estimator. O say, the first estimator is better compared to the second estimator. But then on other parameter values, no? Parameter values, especially we consider the size, sample size. The other estimator or the first estimator is not better compared to the second estimator. Pero kulang naman yung time natin, nag-exceed na tayo sa oras. So I'm going to explain that in a next meeting in this example 7.3.5. Okay, so ano yung natutunan natin dito ngayon, this afternoon? We have the last two method of point estimation. We have the base estimation procedure, and we have the EM algorithm procedure. Okay, so and after that, we consider one criteria of evaluating estimator. We have the mean squared error. Meron pang ibang mga criteria na we're going to learn in the next meeting, in our next meetings. Okay, so that's all for this afternoon. Any questions or clarifications before we go?
Wala na,
Sir,
sir.
kanos ang deadline sa problem set?
Magdugang pa ko ka ng problem set. Siguro karong weekend, maghatag na ko sa inyo problem set para makaset na din ta sa tuang first exam. Problem set sa before sa first exam. So in that way, pag mag-solve mo sa problem set, wala na po mo nagtuon para sa kanyang exam.
Okay, sir.
Okay, so I'm going to stop now the recording.